Hello? Okay.
All right. Welcome, everybody, to the SEEP and Solve event, jointly sponsored by our school PHAISE initiative, which is the kind of a AI initiative for School of Public Health, and also the general DSAI initiative. And it's really great to see that turn up here. And we have a very and also I wanted to say a little bit about PHAISE, and then I'm going to give Brian to give a little bit of introduction about the DSAI initiative. And so PHAISE is a initiative, kind of a little bit informal, but it is initiated by our School of Public Health to sort of start thinking a little bit more about how AI is going to interact with the various type of public health initiatives, starting from education to training. So this is a group of us who meets regularly, maybe once a month basis, to think about what are the things we can initiate to start having discussions about where are some of the AI initiatives needs to go specifically for public health. And one of the things we want to really do is generate synergy with the general DSI initiative with the university's event. And so this is one of the things that we are to bring those two initiatives together. And we have and this is actually the initiative is shared by Greg Kirk, which is our Associate Dean of Research. I am a co-chair. Unfortunately, Greg could not be here today, but I'm very happy to be the moderator. And today we have this is, I think, the first event we are having in the School of Public Health, this type of event. And it's really exciting because we have three outstanding speakers, which is going to really exactly talk about in the interface of the AI and various type of public health and medical applications. So with that, I'm going to ask Brian to talk a little bit about the DSI initiatives and the SEEP and Solve. And then what I will do is that I'm going to introduce each speaker one at a time. And then, of course, one of the main purpose of this event is to actually have drinks at the end. So please, just wait around and have mingle and have a lot of exciting discussions around and solve some problems. That is why it's called SEEP and Solve.
Great, thank you so much. So my name is Brian Capo. I'm a professor in biostatistics, and I'm actually also the Director of Academic Programs and Education for the new Data Science and AI Institute, which is an interinstitutional institute that covers topics like data science and artificial intelligence. It's a large endeavor associated with the large amount of hiring that's going on in engineering right now in AI. In addition, it's created and is responsible for several BDP clusters that are coming about. I would especially like to thank, it has many sub parts of the organization going on right now, some that are focused on research and some that are focused on education and community building. And I would especially like to thank the Colloquium Committee and the DSAI staff and the PHAISE staff all for helping out with this event. So the Colloquium Committee has especially been hard at work putting on events like this one. There will also be a larger spring symposium, which I hope you all can make. In addition, there is an AI ethics and governance meeting going on at 555 Penn in DC, Monday and Tuesday. It is co-sponsored by the Berman Institute and the Data Science and AI Institute. It's filled up right now, but you can still join the waiting list, and things look positive for getting into it, even if you're on the waiting list. So DSAI is currently building up its membership program, and so stay tuned for ways in which you can get involved and become a part of the new institute. It's really an exciting endeavor, and yeah, thank you all for coming.
Okay. Here are our outstanding panel of speakers. I'm going to actually introduce all of them together so that we can go quickly one after another. Our first speaker is Mathias Unberath, if I hope like I pronounced it correctly. And he is a John Mellon Associate Professor in the Department of Computer Science and have multiple secondary appointments in School of Medicine. He leads a group called ARCADE, which stands for Advanced Robotics and Computationally Augmented Environments, which builds the future of computer-assisted medicine by bringing together research on imaging, computer vision, machine learning, and interaction design. And he invents human-centered solutions that are embodied in emerging technologies such as mixed reality and robotics. Our second speaker is Emily Haroz, who is from our own school, and she is an associate professor in the Department of International Health at our own school. And her research focuses on mental health services for low resource and unreserved population. And her training is in psychiatric epidemiology. And she has a background in advanced methodological approaches and study design. And her current work focuses on suicide prevention by leveraging artificial intelligence and implementation science to better serve communities that face significant related disparities. And our final speaker is Thomas Hartung. And Thomas Hartung is he's a chaired professor and in the Department of Environmental Health and Engineering at our own school. And her main goal of our research is to do a paradigm shift in toxicity testing to improve public health. And he brings extensive background in he was the head of the European Center for the Validation of Alternative Methods of the European Commission. And he is involved in the implementation of their vision of toxicity testing in the 21st century. Dr. Hartung's background has a varied background in clinical and experimental pharmacology and toxicology documented in more than 500 publications. We have an outstanding panel of speakers. So without further ado, let us listen from him. First speaker.
Hello, fantastic opportunity to be here. So you see, it says AI lightning talks with a twist. So let's start with the twist. Now, I'm an international. My family lives in Germany, so I visit them frequently. Last year, when I visited them in December, I came back with a gift in my luggage. Because we do Secret Santa gift exchanges, I was transporting a gift that my brother had given me. Obviously, I hadn't opened it because, like you're not supposed to open the gifts before they're due, right? So I was going to the airport in Munich, where they have just replaced all of their TSA scanners with these fancy machines. You probably know them. They are no longer doing 2D X-ray, they're doing 3D X-ray. And in order to keep the load manageable for the people who scan all of the luggage, these systems come with automated AI algorithms that analyze the contents of your bag in order to give these guys recommendations. And so I walked through there confidently because I didn't have anything to hide. And the person working there stopped me, my bag, to this line of shame. And then, like me shortly following my back, and they were like, "Did you bring bananas?" And I'm like, well, I'm a frequent traveler. I have global entry. No, I certainly did not bring bananas. Like maybe you're confusing this because I do have a croissant in there somewhere. So I was sufficiently assured because the person let me go, and I went my way, flew to the US, where shortly thereafter we celebrated Christmas. And so you might be just as amused as I was to find that my brother had actually gifted me something. I'm a runner and climber, and so my shoes are stinky. So he gave me this. Boot bananas, as I found out. Okay, so I found that incredibly entertaining because I connected the dots, right, to the extent that, you know, like that system, the scanner, found it all right. The person got it completely correctly, and yet together they failed. And so this is very interesting, right? So this is the twist, but now let's connect it to why we're all here, talking about how AI is going to potentially assist us in many different ways, especially around healthcare and assisted decision making. Because really the problem that this person using the AI algorithm interpreting these X-rays was solving is a human AI teaming problem. The AI was suggesting something, the human was making up their own mind, and together they were supposed to solve a problem. They got it wrong this time. And it turns out that we get it wrong a lot, because really this human AI teaming is an incredibly difficult problem. This quest for effective human AI teams is really something that these days, now that we have figured out how to build highly capable AI systems, is really where a lot of the very interesting and exciting research is. Because when we're thinking about building these types of systems, we have a whole lot of design choices that we need to be making. And when I say design choices, then really this sounds like it's arbitrage, but it's not, right? We have to justify this in research about cognition, in research about human AI teaming and psychology, really. So the opportunities that we have in order to shape these types of human AI interaction patterns revolve, for example, around the what. Right? So an AI system might give you a clear recommendation. In the case that I was making earlier, it is, there's a banana here. Right? In the case of clinical decision support, it might be the specific genome or phenotype of a disease. It might be a specific diagnosis. It might be all sorts of other things. But that is not the only thing that we might be providing. The AI system might be provisioning additional information, like, for example, explanations, reasoning, additional justification of why the specific recommendation may or may not be correct. There are additional opportunities for us to shape human AI decision-making, because human AI decision-making, just as human-human interaction, is incredibly complicated, right? But those are a little bit beyond on what I will be briefly touching on in the rest of this talk, because we do actually get to talk also about how we are presenting things and when. Like, should we be delaying so that the person has a chance of making up their own mind before we present the additional recommendation, or should we be presenting it right away? How are we presenting it as a transactional style, or do we do something more sophisticated? So all of these design choices we have to make deliberately, and as we will see in just a little bit, they dramatically affect the way how people interact with this type of technology. So the big question that we're not going to be answering today, maybe not in the next couple of years, but I'm interested in touching upon and maybe discussing with you later, is how can we create these effective AI decision support tools that enable humans to perform well? There right now are two cultures. I'm in computer science, so this first culture is usually the one that is incredibly prevalent among engineers, and that is the technology first culture. It is very much focused around the idea that, well, creating explanations, creating human AI decision tools is a very complicated technical problem, and so I need to build very sophisticated tools in order to enable this. The human is an afterthought. There is another culture that is more human-centered, design-based, that exists in fields that nowadays are native to computer science, like human-computer interaction, human AI interaction, but is also grounded in psychology, behavioral psychology, and cognitive science, that really thinks more about this problem from a human-centered perspective. So what are essentially human patterns of behavior that we can exploit and leverage in order to design effective tools? They say that technology should come after, because first I need to understand what technology will shape a desirable behavior. And once I have identified what the opportunity is, then I spend the effort in building the tools. Both of these are important. You can make up your mind where you are. Personally, I am a firm believer in the second approach. Let me show you how some of these ideas that I just posited, the fact that human AI interaction is complicated, affects human AI decision-making for medical decision-making tasks. With a collaboration here in the Wilmer Eye Institute, Justin Johanan, who is a professor there, we have a long-standing collaboration on trying to prevent blindness due to glaucoma. So glaucoma is one of the leading causes of blindness, and identifying people who suffer from glaucoma and will progress rapidly is incredibly important. Some people progress slowly, so you have many opportunities to give them the appropriate care. Some people, once they have disease onset, they progress so fast that it's incredibly hard to catch them early. Not everybody can be seen, especially early on in the disease, by glaucoma specialists, which essentially means that what we want to be able to do is we want to enable providers who are not specialty trained in glaucoma to detect people who might be, deteriorating rapidly so that they can be priority seen by the specialists. This is not something that these people are trained at, so it's a very complicated problem that is slightly beyond what their regular training comes at. So they will certainly benefit from assisted decision support that we can provide through AI. Now, what we're studying here is how we can enable these people with providing AI systems. What way and what information should we be providing and how in order for them to get it right? And we ran a user study that essentially was studying 4 different paradigms on how AI might be provided. The first paradigm is something where we don't provide any assistance. We provide the metrics that are currently being collected as part of routine checkups, but we don't provide any additional information, no additional recommendation. In the second one, we provide a black box recommendation. So the AI system, all of the information that we saw before, but in addition, the AI recommendation will be presented to say, well, this is a patient that needs urgent referrals. We also built one that has a post hoc explanation where not only we provide the recommendation, but we also provide the 3 high risk factors that contribute to the model making this recommendation. So there's a high pressure, there's a low average thickness, and low mean deviation, so they see poorly. And then there's another model that we built, which is this intrinsically explainable model that uses a scorecard where you can see how individual factors of that person's behavior, so for example, the age, the intraocular pressure, the mean deviation, so how their visual field essentially, and other things, how they contribute and how strongly they contribute to the personalized prediction that we're giving them. Right? We then recruit about 90 optometrists, so primary eye care providers, to perform this study and tell us how they feel when they interact with these systems to make predictions about individual patients. And what we're finding is that was fantastic, right? So the performance dramatically increases when these people use AI. So that's great. And the agreement, so their agreement with the AI recommendations also increases when we provide explanations. So explanations is great, right? Like not just a recommendation, but we also say why. But look, here's the downside, right? All of this sounds great. But as I mentioned at the very beginning, human AI teaming is a complicated problem, right? This is the upside. Now, here's the other side to this. While users perceive that they incorporated AI, in reality, what you find is that they didn't really incorporate it. They essentially just experience over-reliance and automation bias, right? So they essentially just say and echo what the AI is saying. They're not leveraging the explanations to the extent that it would allow them to make up their own mind, right? And really tease apart when the AI is correct and when it is incorrect. In fact, the human-machine teaming performance, so the human working together with the AI system to make recommendations, is worse than just having the AI system operate, in this case, alone. So really, we're not, like, when we're thinking about, right, leveraging complementary strengths between humans and machines, it's not here. And this is not the only study that is finding this. So the human-machine team, right, we can build a sophisticated explanation, we can build a sophisticated algorithm, but enabling the human to do better than the machine alone, we're not quite there yet. So really what this means, right, is that our quest for effective human AI teams, just as in the example that I introduced in the very beginning on detecting bananas in my luggage, it continues. We're not there yet. What are the design choices that help us shape desirable interactions? What is the what, the recommendations, the explanation? What can we do about the how and when we time this information, the presentation style, such as wording, the sequence of these interactions? So really, how can we create these effective AI decision tools in order to support humans that are at the center of pretty much everything that we do? Because the reality is, right, that AI and machine learning technology is here to help us positively transform healthcare. So we got to make sure that we're prepared. Thank you very much. I'll stick around. You can find me for discussions. Do I have questions or no?
Maybe a couple of questions to gather some time. And then make it time to discuss further.
Yeah, so just say, yes. So like you show that like just using AI is like about 70% better than human AI. Is there any reason why, I mean, like we intuitively as humans we believe that we can, use AI and perform better. But what is the argument around, why don't we just improve the AI to like 90% instead of like we need to somehow sneak in human there? Is there like an argument that like, why do we actually need to for human?
So there is a very solid body of evidence that suggests that in high stakes decision-making scenarios, which medicine is one of them, humans vastly prefer, like humans in the sense of not the person that makes a decision, but the human who is at the receiving end of the decision, vastly prefers a human to be at the end of the deciding chain, right? There are examples in many of these things. Humans are not that transparent. Like, the reason why this is complicated is because humans are not as predictable as you think they are, right? And so there is a big body of evidence that suggests that in stakes with a whole lot of inherent uncertainty, as well as in high stakes scenarios, humans prefer a human to make the final decision. So they are okay to accept automated decision makings or automated decision makings, so fully automated in stakes that are not high risk, but they really don't like it in high stakes examples. So for example, if you were to use an AI to screen applications for a job posting, screening applications is fine. Making the hiring decision is not, right? So there are studies on doing exactly this. And then the additional problem is that in some cases, you might simply not be able to create an AI system that has that accuracy level that always surpasses.
Bananas. I guess like the question, right? Like, is that really a failure, right? It was bananas, it wasn't a weapon. And so you had a human taking the input from the AI, taking the input from how you reacted to that response, and making a human judgment that, like, whatever, this guy says it's not bananas, I guess I'll take his word for it. Maybe the line behind you was long. I mean, that seems almost like an appropriate human response to the data that they had. And so I guess I just love to expand on that.
Well, I mean, first and foremost, I find it just incredibly entertaining, right? So of course, right? Like this is a very low, in that specific case, it's a low stakes scenario. So whatever comes of it, it doesn't really matter, right? And you might find different scenarios like that in a healthcare and a different use case as well. I mean, really, the reason I chose this is just to set up the slightly bigger discussion about how do we deal with scenarios where the stakes are high. Because in the high stakes scenarios, right, this hand wavy, like, yeah, maybe it's not that bad after all, is not usually an acceptable answer, right? And in those cases, we just don't have the tools to get it right a lot of the time, right? Which is, I think, really the major point that I'm trying to drive home, is that there are a lot of assumptions being made, right? Like this assumption that we should be investing in explainable AI and so on, because that's where the future is, in order to make sure that people can properly calibrate their trust. Well, actually, much more research shows that people cannot calibrate their trust. It's very, very complicated, especially if you are dealing with things that are under knowledge imbalance, right? Like this person could have gone back and actually check the CT scan themselves, and they would have gotten their own answer, right? In some cases, we're relying on AI systems that perform a decision making where the user cannot go back and make up their own mind. It's impossible, right? So it's very, very complicated. This whole navigating this whole space is very, very tricky, and we don't have good tools at all. Yes.
Awesome. Well, that's a great intro to mine talk. So thanks for doing that. And we're navigating a lot of those same decisions as we work in our project. So I'm going to talk a little bit more and take you outside. So I do most of my work at the Center for Indigenous Health, which sits in our International Health Department. And I work a lot on health equity related to suicide prevention. So I'm going to just talk a little bit more about some of our work and also these struggles we're navigating. So before I begin, I think this is an audience that maybe doesn't always hear this, but when we think of AI, we're using data. And really, data is a powerful thing, as we all know. And this is one of my favorite quotes from the director of the Seattle Indian Health Board. And she says, data speaks, it sings, it carves, it paints, and how we tell the story is very powerful. So I like to just situate ourselves in that sort of lens as we go forward. And I have learned a lot about this in my own work as I situate my work in the context of history and continued abuses about how data is misused, stolen, and misinterpreted or flat out wrong. So these are some headlines. So on the right here, you can see a headline from the 1970s, I think, when a community in Alaska invited researchers in to sort of understand why alcohol was affecting their community and what they could do to stop it. And instead, the New York Times got a hold of the story and published this article that really used stigmatizing language and sort of stigmatized the whole community as alcoholics. And this was based on certain findings in that study, but really how it was shaped in the narrative really wasn't welcomed by the community. More recently, the Havasupai tribe ASU worked and actually stole a bunch of data and allowed DNA data to be used by other groups for different research questions. And then this is an example really from the from the last presidential election, where you can see basically like Native Americans are left out as an entire racial group here in the United States, among many others. And so just like how we think about data really matters. And of course, it's not limited to Indigenous populations. We're steps away from Henrietta Lacks and the legacy of that, where her cells were stolen without her consent, and then were sold and used for many discoveries in science. And the family didn't really get payment for that at all until recently. And then hidden harms, so we're using algorithms and we're identifying LGBTQ students who might be at risk of suicide or other types of violence in schools. And in fact, that's also happens to be outing them on social media platforms. And then just as you can see, algorithms rule our working lives. These are everywhere. And I don't think I need to tell everybody about these studies, but this is also in healthcare. So this is the Obermeyer paper that I think many people have seen, really focusing that at a given risk score for a widely used algorithm, Black patients were considerably sicker than white patients, and thus considerably less likely to receive care. So the data we use are perpetuating these inequities in care. In my own work in suicide prevention, this is an article by Yates Collet, who showed racial ethnic disparities in the performance of prediction models for death by suicide after mental health visits. And these are ROC curves. For those in biostats, you might know these, but really showing the predictive accuracy or a rough approximation of that of our algorithms. And you can see that for certain racial groups, including American Indian, Alaska Native, and Black and Hispanic patients, it's performing quite significantly less than other populations. So there's been a lot of work thinking about how do we address bias in our algorithms. And this is a nice scoping review done by Carl Thomas Berdahl and all, looking at sort of all the different strategies people have used to think about bias. And you can see there's ones we all talk about, the actual data itself, right? We're going to have a whole symposium next week on this. The sort of bias ingrained in the data. You should improve the diversity and quality and quantity of data. But one of the things they also mention is really engaging the broader community. And I think about this both in the human-computer interaction. I think that literature leads into this, but also more broadly in the patients themselves, the communities, the communities we work with. And so with that, I'm just going to highlight a little bit of our Native Rise project and how we've been doing that in communities in the Southwest of the United States. So first, just to give you a scope of the problem of suicide in the country. So these are deaths per 100,000 population, and you can, over time from 2010 to 2021. And you can see sort of on average, our rates have gone up pretty steadily for all races. There's a little dip in 2020 and then kind of gone back up. But for American Indian, Alaska Natives, you can see that their rates are just above everybody else and continuing to climb dramatically. What this tells me is we should spend a lot of time thinking about and working with communities to develop solutions around this. So back in 2017, we were funded by a small grant from the Bloomberg American Health Initiative here because the tribe approached us about a problem they were having. They're running this amazing surveillance system that basically looks at anybody who's at risk of suicide, gets referred to community health workers who go out and try and find them, provide them support. And there has been some dramatic drops in suicide rates because of that system in place. And in 2017, though, the system was continued to get more referrals. So people kept saying, like, we know this system exists. And that's what you want. You want people to be reaching out. You want them to get help. But at the time, it's a large geographic area. It takes about 2.5 hours to get to the farthest point and back, about 5 hours to the office and back to find people. And they're doing in-person visits. And we have a limited staff in these large areas. So they asked us sort of, is there a way to tell who's at highest risk? Making sure that we find those people first. And so that led us, and I'm an epidemiologist, just learning about machine learning, to think about how do we actually do that? And so we developed an algorithm using local data, surveillance data, and we found quite a high area under the curve of 0.87. And that's all good, but then to Mathias's points, we thought about, like, how can we actually use that algorithm? What's going to take to use it? So we talked with case managers to inform its implementation, and we worked to implement it. Given the data infrastructure they have, they run this on REDCap. So we're looking at like a logistic regression model type of thing in REDCap. We then wanted to pilot test it to look at, like, is the algorithm actually accurate as we roll it out into care? So in new data. Does it improve the reach of care, which was really the goal of the project and why we were asked to be involved? And does it potentially reduce risk for those people that we visit more often, because we're actually identifying those in care and trying to reach them and provide them the services they need? And then I'll just briefly talk at the next one is, now we've gotten some funding to actually expand this to the health system, to Indian Health Service, which serves 2.2 million people annually and is the largest health system for American Indian Alaska Native people in the US. So I'll just highlight a little bit of the results of implementation. These are kind of complicated tables, but what we found was sort of before we implemented it, just in sort of, it was running in the background on new data, that, and these are small sample sizes, that the algorithm continued to classify people at high risk well, and that it was much better than anything we had in existence. So a single known risk factor, suicide attempt, having a previous attempt is the biggest risk factor for a future event. And that did not show us any sort of differentiate people in any way, but the algorithm did. And then what we did was we looked at sort of the odds of repeated suicidal behaviors during the period when the algorithm was inactive for these high risk cases. So if the algorithm said they were at high risk, but we hadn't let the case managers know that yet, that was the inactive period. And then there was a period where we actually turned the algorithm on, the case managers started using it, and that's what we call the active period. And just the highlight here is really that what we found was it improved our reach of care, obviously with a very small sample size, and that it actually reduced risk among our highest risk patients. Presumably, this means that we were flagging people. That made the case managers go and attend to those high risk patients and provide them with care, and that sort of extra contact was reducing their risk of future events. So this was all good. Again, small sample sizes, really pilot work, but we got the R01 to expand this to the health system. And I'm not going to go into a lot of like math here, but I'm just going to talk a little bit about the algorithms we've been working on. So we have some algorithms developed. Mainly, again, we're using logistic regression and random forest. This has a lot to do with the IT infrastructure that we work within. So thinking about how do we design models that actually run in places that don't have great access to servers or computational support. What we found is our models significantly outperform a baseline, and that baseline includes like anything a clinician would use to identify someone at risk of suicide. So oftentimes in hospital settings, people are screened. They might have risk assessments. A clinician might say, oh, they had a previous attempt, so lifetime history of attempt, or a previous ideation in the last 90 days, so they're actively struggling. And even when you combine all those things together, the algorithm does better in terms of accuracy. So we have a good result here. We're working towards implementation. And as we do that, we're really thinking about how we can use community engagement to improve the relevance, rigor, and reach of our work. And borrowing from the total product life cycle, which is the FDA guidance on sort of what happens with a model as it launches towards implementation, there's several steps along the way: conceptualization, design, development, validation, access, and monitoring. We've been thinking about different types of community engagement at each of these steps. And so I talked a little bit about how the tribe came to us for this request, and that our community members really identified this as a problem. And so that really helped us with the conceptualization process. During the design process, we're really using data from a locally relevant source that's really highly specific to this population. We're doing in-depth interviews with community-based providers. That helped us shape how to implement it. Where does it come in their workflow? How do we actually provide that information in a way that makes sense? As we go towards developing it towards this R01 and launch it in the health system, we're convening local advisory teams. We have in-depth interviews have been shaping the implementation. And we continue to talk with community providers. And so we've made a lot of the decisions that Mathias pointed out, like, when do you show this to a clinician? What information do you show them? A lot of what we're learning is also that context really matters and the implications of those decisions really matter. And I think this sort of high risk, low risk stakes is like, what actually happens with this information? Is it that somebody's getting involuntary committed, or is it that you're administering a new risk assessment or just asking the question again in order to like open up that conversation? And so we're working through all that. And as we sort of set out to validate the algorithm, again, we have a new tribal resolution to support this work. We have these community advisory boards that are providing ongoing information. Then we're doing interviews with providers, as I mentioned, but also with patients. It can be really abrupt to come to the ER with a sprained ankle and then be told you're at risk of suicide without disclosing that information. And so really talking to them about what this means, how do you want to be talked about, and then making sure we give that feedback to providers is really important. So I just say that like the big thing that we've been working on, and I think I would encourage many people to do, I know it takes a lot of work, but it's really hopeful that the work we do is really rigorous and relevant to the communities we work with. And so just like incorporating community engagement at all of these stages. Ultimately really thinking about how we want to improve outcomes for all. And if we continue to focus on only certain populations or data with certain, or populations with certain data, that we're going to miss out on really the highest risk groups. And to do that, really making sure that the models that will touch people really are involving their input at every step of the way. I'm going to say thank you, and just huge shout out to our colleagues who are doing a lot of work with us on this.
Hi, thank you.
Yeah.
What's the structure of your surveillance data, and how do you integrate the interview with the local providers with the local people, and do you process those interview transcripts as a natural language, or you that help you with the data processing and collection procedures?
Yeah. Thank you. So the surveillance data is actually the only community-based suicide surveillance system of its kind in the world. So it's basically anybody can be referred to the surveillance system if they have any risk. It can be referred by anybody in the community, and there's a tribal law that mandates that. So if you know somebody's at risk of suicide in various ways, you're supposed to, by law, report that to this team. The data structure is actually like a longitudinal data set. And so there's like a registration and then multiple sort of events that can happen on with a person. And then in terms of the interviews, so the case managers really use that and sort of go out and find people and try and do follow-up visits with people after an event like this. We are not using AI to analyze our qualitative data. and it's all in English, but we are using a lot of like community interpretation with that. And so we sort of do the findings and go back to our partners there to really make sure that the findings we have make sense and are relevant to the context. Thank you. Yeah.
So speaking of context, which I
Yeah.
love that you brought that in, I noticed your active period during your pilot study was during COVID.
Oh, yeah.
Almost.
It was.
So can you talk a little bit about how perhaps the performance of your two approaches, religious regression and reinforced, what your intuition is about the performance in that pilot and how that may be different in kind of a post-COVID?
Yeah, no, it's a great observation. I appreciate that. Normally I highlight that March 2020 was our launch date, which was not a good launch date for a study. And again, it's a pilot study. So, I mean, I think what we hear from our case managers is that it makes sense for the most part that people were flagged as at risk. And when you look at the features in the model itself, they're not like random things. They're like pretty theoretically driven. So we actually have a paper that's about to come out that's focused on taking algorithms from outside of these contexts and seeing if they fit our data and performed well in our data. And what we took two models, and what we found was the one that's really based on sort of administrative, like just data, everything in it performed terribly, but the one that was actually theory driven in terms of the features it used performed really well. So I think inevitably, and we're about to run a randomized control trial on this, which I think is actually like a whole other, we should have a whole clinical trials and AI symposium, because that's really challenging to do. And it's been really interesting to sort of think about how to design that. And so hopefully we'll get some answers. I think like, cause we're using theory-driven features, I have more confidence in it. And then I think just in general with the RCT, we'll actually be able to maybe even see this without sort of the impact of COVID. Yeah.
Thank you.
Thanks.
Last talk,
Yeah,
Thomas?
thank you.
So, yeah, when NVIDIA became the most valuable company in the world, I was told AI talks should be given a leather jacket. So you see me. Okay, I make my slides available. I have the QR code also on the last slide again. And this is Eric Johnson, who is leading with me a SURPASS project between the Applied Physics Laboratories and the Whiting School of Engineering. Yeah, AI at the moment is everywhere after 70 years, which is astonishing. But this is the synergy of three things. The data of the world are doubling at the moment every 18 months, or you could say 90% of all data in the world have been produced in the last 3 years. Our computers getting more powerful. For 60 years, Moore's law holds. Every second year, our computers are twice as powerful at half the price. But the most incredible development is AI. Since 2010, when deep learning was introduced, the AI capacities are doubling every 3 months. So I came into AI 10 years ago when two students joined my team, Alex Mertens and Tom Lichtefeld. They came with machine learning backgrounds. 10 years ago, this means since then, the power of AI has increased 1 billion-fold, 8 to the power of 10. 8-fold is also roughly the difference between ChatGPT 4.5 and 3.5. And just to make you understand how much this, what this results in, the latest ChatGPT model performs at an IQ of 126 in the Hamburg-Wechsler intelligence assay, stably. So this is something to reach first. In these 10 years, I had a lot of privileges to assume roles then in AI, thanks to the hard work of my team. I became field chief editor on Frontiers in AI. We organized a Keystone Symposium earlier this year, and I was working the last 2 years with the World Economic Forum on some aspects. I'm saying this mainly because this allows me to also take a bit more of a 10,000-foot perspective to these things. Our bread and butter work, however, is into toxicology. That's what the Department on Environmental Health and Engineering of both the Bloomberg School and Whiting is about. We are trying to use AI to make big sense with big computers from big data. That's what AI is about. AI does not only shine if you really have tons of data, diverse data, very different type of things. Everything which is an Excel sheet is not really needing AI. These are a number of papers which I make available. They're all open access, which are describing how this is transforming toxicology at the moment. But I want to talk today not about AI, but organoid intelligence. I have to quickly talk about what is an organoid. An organoid is a system which is formed from typically stem cells, human stem cells, which are self-developing into organoid structures, which are reflecting some of the architecture and of the functionality of an organ. So not just a petri dish with cells which look like pan-fried eggs sunny side up, but something which is reproducing this. The FDA has coined the term microphysiological systems because they are micro and they are physiological. These are is an umbrella term. Over the last 4 years with our team, we have created an international society and a series of workshops. I don't have the time to go into any details, but it is just to show you over the years, we have been very much involved in workshop series and conferences. One of our workshops even resulted in a science paper on how these models are at the moment fueling drug development. And in the years 2022 in New Orleans, last year in Berlin, and this year in Seattle, we carried out with our team here out of Hopkins 3 world summits in this field. Our own work was stimulated by autism. You see here a figure which is showing how autism in the US, according to CDC, is increasing. From 1 in 10,000 to now 1 in 36, according to the last statistics. 1 in 36 children now being diagnosed. And this is no longer explainable by genetics. It's no longer explainable by increased awareness and changing diagnostics. There must be also lifestyle components and exposure. This is one of the things we are interested in working on. So we are interested to find tools to do this. And out of this interest, we started to get interested in brain organoids. This is not our brain organoid. Unfortunately, half a year before we published our brain organoids, this Nature publication showed how to do brain organoids. And their paper was much better, I have to admit. Still, we came up with a different spin. We showed a few years later how to mass produce brain organoids. So they're really looking like these balls. And out of 1 6-well plate, we can produce up to 4,000 of these brain organoids. And we made it on the front page of the Financial Times at the time, mass-produced mini brains to spark rethink over testing on animals. And this is exactly what our work is about. We are a Center for Alternatives to Animal Testing here in the school. We have been using since these brain organoids for autism research. We used them to first show that human neurons can be infected with COVID-19. And we also, for example, grafted them with glioblastoma. Again, we don't need to talk about details here. These are some publications. It's a summary publication of earlier this year. Lena Smirnova, here in the audience, knows everything about this, and her team of excellent researchers. They do fantastic stuff with these brain organoids. I want to show you now something crazy, which I think is lived science fiction, which is we are trying to talk to these brain organoids. Like AI researchers at the moment are trying to talk to animals, something no human can do, but AI is starting to enable talking to whales, talking to other types of animals. We are trying to communicate by combining AI. And this is actually a possibly disruptive technology because it is possibly establishing memory and learning in these systems. So that we have human type of intelligence in a petri dish we can study. So we call this organoid intelligence, OI. It would be establishing models which are showing the cellular and mechanistic foundations of simple learning acts. They allow us to test how electrodes, how microelectrode arrays can be interfaced with these brain organoids, the type of things Neuralink of Elon Musk is trying with patients. But I'm mostly a toxicologist and pharmacologist. Imagine if we can build disease models now, disease models of cognitive misdevelopments of neurodegeneration, we could suddenly start looking into these, or what is fueling Alzheimer? Is there chemicals involved? Is autism really something which develops or is aggravated by exposure to chemicals? And the engineers are dreaming of biological computing. They're dreaming of using the power of the brain to build even better computers. To illustrate this in a simple fact, the computational power of a single brain, which is estimated at 1 exaflop, was reached by a supercomputer only 2 years ago. And this was a $600 million supercomputer of 6,800 square feet of installation to get the computational power of a single human brain. Okay, to illustrate organoid intelligence, let's start with work by others, our friends and partners from Cortical Labs. They published in 2023 that in vitro neurons learn to play a simulated game world. What you can see here is the game Pong. If you're as old as me, you will recall how excited we were when these computer games came onto the Christmas tree in the 70s. This pedal, however, is controlled by brain cells, by neurons. And they could show that these cells actually improve in each and every session. They get better in controlling this ball. This paper was published with an editorial from Lena and myself. We are working very closely with these people because they have found an intriguing way of measuring memory and learning. However, what they did not really stress is that their cell system is only learning for a short period of time during the session. Next day, they start from zero. They cannot memorize. They have a short-term memory only. Because different to the brain organoids, they don't have the infrastructure for long-term learning. So what is different between a cell ball like ours and their culture? First of all, we have glial cells. In the meantime, up to 50% glial cells. We have myelination, which means oligodendrocytes are wrapping themselves around axons. But the glial cells are particularly important to prune the connections which are not necessary. And by this, they form the long-term memory. One neuron is on average connected to 8,000 other neurons. And memory is established by taking away all the weak connections. And the density of a three-dimensional culture is about 1,000 times higher than a two-dimensional, which allows many more of these synapses to form. Starting work is Brian Caffo. You heard him talk earlier. David Gracias, our partner in biomedical engineering, created these type of shell electrodes, which are embracing our brain organoids and allowing a type of EEG. This was a publication in August of 2022. And this is how we envisage this to become a really high electrode density system by moving into the three-dimensional case. And we can do also then pharmacological work. You can show that this has really a very nice resolution. Signal-noise ratios are very nice of these systems. We published the concept of organoid intelligence in February last year. We've never had such a reaction to an article. We had 600 press hits from CNN to BBC to Financial Times and Wall Street Journal, Forbes, name them. Everybody was reporting on this concept. So this was really a balloon which was going up loudly, and now we have to show it is not imploding silently. It was very quickly taken up by the White House. They made it one of the bold biotechnology goals of the US to produce such systems. And we were able also to convince the National Science Foundation to call for engineering organ intelligence in an open call. There's even a children article about this. So if you're interested, this is meant for 12-year-olds. We can provide this article. We combined this with the call, the Baltimore Declaration towards exploring organoid intelligence. We carried out a workshop, how to form a community. There's a new journal, Frontiers in Organoid Intelligence. This is the call, but we have now also newsletter and website. So we're really forming a community. I think so far this is about 450 people who have signed up to get information about this. The university was very generous in supporting our work in 2 Surpass grants so far and a discovery grant earlier. In this collaboration, which also involves the ethicists from the Berman Institute, we have first of all increased the glia cell numbers to physiological levels of about 50%. It's the only system I'm aware of of humans. We are scaling the system from some 500 micrometer, which is just barely visible as a snowflake, to something which is now half of a centimeter to a centimeter, which is then already twice a mouse brain. For this, we need perfusion. There's a lot of work going on. We establish electrophysiology of different kinds to measure what is happening in these systems. And we believe we have some evidence of what is really leading us to long-term memory. Especially, we see that after feeding information into the system, the brain is reorganizing from random connections to orderly connections, which is called criticality. We see early genes of learning are being introduced, and some modulation with drugs is also possible. This is how it looks. This is our game environment. This figure is controlled by a computer, by a brain organoid in our laboratory, and the analysis is taking place in the applied physics laboratories down in Silver Springs. And we can measure how long does it succeed to meet this parcours. This little robot here is in David Gracia's lab. It is controlled through Bluetooth from brain organoids in an incubator and is trying to find its way in a parcours. This is the type of physical experiment we're trying here. You can imagine that this has a lot of ethical implications, probably not with these snowflake-sized brain organoids, which have as many neurons as a housefly, but it is probably, if we are going to larger systems, if we are training them with more relevant data, we cannot exclude that at some point self-awareness, some type of consciousness would develop. And for this reason, we are excited that we have in an approach of embedded ethics, ethicists working with us. They meet with us in our weekly meetings, discuss experiments, and they come to the lab and they get very humble if they see these tiny little things and the simple experiments we are carrying out. A summary here of ethical, legal, and social points of view earlier this year. The exciting part will start afterwards, and this is what we are preparing for with a number of groups here in our school and Hopkins and beyond. We are trying to develop disease models, because this is, for me, the exciting perspective to use this for finding reasons for models for Alzheimer's disease, for amyotrophic lateral sclerosis, for autism, for some rare diseases like leukodystrophies with Kennedy-Krieger and UPenn. And we hope to form now a dementia OI research initiative, which we term DORI, as you can imagine now. So somehow, this is an unusual project. I call it lived science fiction. And actually, when I gave one of the first talk, a friend and colleague gave me this link. He said, you should see Star Trek from 1966, because in this episode, Captain Kirk is finding this brain-based computer. So unfortunately, I have to tell you at the end, there's nothing new under the sun. Everything has been thought before, and we are only following these. So with this, I would like to thank our brain organoid team, some really excellent scientists in Hopkins, and quite a group forming from outside collaborators, which are following this joint vision. And again, here's the access to the slides if you want so. Thanks a lot.
Thank you very much for the talk. As we have been talking a lot about the ethical concerns and how it could be translated to many diseases. I wanted to ask if we could have more developmental defects in brain organoids and actual brain. Is that some space that someone is exploring? Because developmental defects throughout the stage that a brain is able to perform is also something which could create more problems or solve more problems. So which spectrum are we? More problems or less problems?
I hope that we can model the real problems, the real world, what we call validation. So we are interested in calibrating our models against disease phenotypes. We see really these brain organoids like a living biopsy. Yeah? You can, from a patient, you can typically not get any sample of the brain. but you can get skin or blood cells and then grow brains from this patient. So this is what we are doing in many of our projects now with with various diseases, in order to use then the functionality as a readout. Sure, there can be artifacts. Every culture system is an artifact. All models are wrong, some are useful. George Box has said so wisely. This is what we have to find out. But if we are able to show in these systems that a disease can be modeled, we might also be able to redirect the disease. Like chemicals are aggravating the disease, there might be the good chemicals which are bringing us back or helping us to prevent in the future. So I'm on the optimistic side of things. I always see the bottle half full.
Thank you for the talk. That's very impressive presentation. I'm just wondering whether this organoids, first of all, can be programmable in the sense that, you know, maybe like plug it in and then write a bunch of code.
No.
But number two is whether how scalable are these organoids? How do you create that at scale? Yeah.
I'm not thinking that it is in any way a problem to manufacture these type of systems. Stem cell culture is expensive, but as I said, 1 6-well plate gives you 4,000 of them. And I think this is only a matter of a market need. However, it is not a computer. You cannot clone, you cannot program, you have to train and learn. It's like a little human. It will have also a lot of things which are unique, will never be reproduced. Even if you standardize the training of these brain organoids, they will bring in individual components which are just artifacts, like we are. So one brain organoid has not been fed properly, and it will leave a mark. Like famine has left a mark on many people in epigenetics, and we will observe a lot of these things. We should not expect only that these can do things human can do. We can also think about super microphysiological systems, supernatural ones. We could create one of the 10-kilogram brain, too heavy for you to carry on your body, but in a computer setting, you might have it. We can have, we can start with synthetic biology to modify this. We can give inputs which no human brain gets, like optogenetics and others. So we might really think about systems really more as a synthetic biology thing. And for the engineers, it's really about neuromorphic computing to understand why is the brain so efficient? How does it realize progressive learning? You learn a few new words in Italian, let's say, you just integrate this. Most AI needs to run a new model if you want to integrate new data. So it is very interesting to do this. Or how do we establish intuitive thinking? You can intuitively, quickly react to a situation. Computers can't. They have to run through their algorithm. These are the type of things we hope to possibly learn from the brain. But even if it's not a vet brain which gets, I don't believe you will have a laptop which gets 10 milliliter of cell culture medium per day. But I think we will be learning something also for computer sciences. Good.
We'll close the formal session, but please help yourself to mingle, and then there's nice drinks. And let's thank the speakers again. All the speakers.